We're going to take a specific example now and take a look at what linearization means in this case. So we're going to have a square root function. It's been moved to the left 3, so I'm just making a quick sketch to give us a visual. There we go. And we know that when x is 1, then the y value of this function is 4. We didn't need a calculator to do that. We just plugged in x equals 1 here and found a y value of 4. So we have 1 point here, 1, 4. I want to approximate this curve as a linear function at this point when a equals 1. So that means I'm finding the slope of this tangent line right here. And no, oops, I should have this point right here. Notice that when we're close to here, it's they're nearly the same, the straight line and the curve. That means I'm going to find the equation of the tangent line. So the equation of the tangent line is the derivative, or y prime, which is 1/2 times x plus 3 to the negative 1/2, times the derivative of the inside, which is just 1. And I want specifically find the slope of the tangent line at x equals 1. So prime at 1. And that means that it's 1 over 2, 1 plus 3 to the 1/2. And if I use my radicals instead, I can maybe see what that is without too much calculation, too much difficulty in calculating. So 1 plus 3 is 4. Square root of 4 is 2. So that would be 1 over 2 times 2, which is 1/4. So this slope is a slope of 1/4. The equation then is y minus y1 equals slope and x minus x1, just using the slope point form. So y minus 4 equals 1/4 x minus 1. So isolating the y, and then I can simplify this if I like. It would be 1/4 x minus 1/4 plus 4. And if I make this a common denominator, I've got to multiply both top and bottom by 4. So in the end, I get 1/4 x plus, this is 16, and minus 1, so it's 15/4. So what we're saying is that this equation, the y equals square root of x plus 3, can be approximated to be this linear equation as long as we're very close to the answer, an x value of a. And that allows me to say, well, what happens if a is 1.01? Well, that means that I'm very close to 1, and I could just plug in 1.01 in here and figure out what my y value is, and not have to plug it into this. And notice I wouldn't need a square root on a calculator to figure that one out, and that's where historically there was strength in learning how to linearize. Let's do this for a second example, and I'm going to take a log example. So y equals the natural log of x, and I want to figure out the linear approximation at x, or a, equals 1. So using a sketch just to help me get a picture of it, here's my log graph, and at 1 I've got 1, 0, and I want to find the linear approximation. So what does this line look like? I am going to use my formula, which is really just the equation of the tangent line. I just made a mistake there, sorry, which is x minus a, and you might see it in your textbook as x minus a plus f of a. So I'm just moving using all my symbols instead of plugging in the numbers at the beginning. So I'm just moving the y1 over and calling it f of a. So in this case, a is 1, so I want to find the derivative at 1. The derivative is 1 over x, and when x equals 1, it's 1 over 1, which is 1. So that means y equals 1. There's my derivative slope. X minus the a is also 1, plus the y value at 1, which is 0. So my equation is x minus 1. That means that this line here, y equals the log of x, can be approximately estimated as x minus 1 as long as we're close to the value of 1. So that means I could easily figure out what the log of 0.99 is. It's approximately equal to the 0.99 minus 1, which is 0.01. And you can try on a calculator now doing the natural log of 0.99, which, that should be a negative, sorry. It is, if I did this straight up on the calculator, you get equal to negative 0.01005. Notice how close we are with our estimate, and that's because we are very close to x equals 1.